Why wouldn't you want it to converge quickly?
Oh, I wanted to converge quickly, right? So if it converges quickly, that means I can increase my delta t because I don't want to be stuck with a delta t that is really small. And you're going to see from the solution what that means. Okay, so if I Newton less than that, and let's see, delta t is less than 0.1. So because we don't want a huge delta t really, even if it converges really quickly. All right. Any questions? Okay, so let's now run this. So now let's plot this again. Oh, yeah. Now we have a t, right? A vector of t. So here's what we get. All right, actually, initially we can see that we are dropping to this a value of minus 1.8 really quickly, right? So initially we can take a bigger step, and then it finds out that the change is really fast. So we are taking pretty small steps over here. And then afterwards, we are also then taking bigger steps again. So let's actually relax this a little bit. So let's make it 5 so that when we run it, we can actually see that we can get away with a pretty big step in this slow moving region. Okay, and in fact, if we advance for not just 300, let's do it for 3000. Okay, it finishes equally fast. We plot it. This is the kind of solution we get, right? So it's punctuated equilibrium. The solution goes back to around the -2. It slowly goes back to 0, then suddenly jumps to around +2, then slowly goes back and jumps back to here. And actually, one thing we are missing here is we had our time step determined by how fast the Newton's method converges. One thing we are missing to get a real professional ODE solver, another thing we have to do is to assess the accuracy of the step, right? My delta t should not only be determined by stability, but also by accuracy. That usually means comparing two different time integration schemes, right? So here we use backward-Euler. If we have backward-Euler and another time integration scheme and compare against their solutions of that time step, then we can more intelligently determine what delta t we should use. Okay, so here in reality, I think the time steps I'm using over here is probably too coarse, and if you use and that actually affects the accuracy of the solution. If you use MATLAB's ODE solver, you're going to find out the solution behaves qualitatively like this, but quantitatively it's more accurate. All right. So any questions on the code like that? Yes.
What is the I-try doing? Like, what is that loop for?
The I-try loop is doing multiple delta t's, right? So when I is equal to 1, delta t is adjusted over here.
Okay.
Oh, adjusted. Sorry, not over here. At the end of the I-try loop.
Okay, gotcha.
Right. So initially I have the delta t that I used at the last step, and if when I-try equal to 1, I do 12 Newton iterations. If it converges, then I exit the I-try loop. If it doesn't converge, if 12 Newton's iteration doesn't converge, then I cut delta t to half. Then I-try is going to be 2, right?
Okay,
I'm trying
so
the second time.
Converge, like after updating it 4 times, then it just like stop.
Well, it should. I mean, when I cut delta t, unless I have a bug, when my delta t is small enough, Newton's method is guaranteed to converge, right? Newton's method is guaranteed to converge when my initial guess is close enough to the final solution. So when my delta t is small enough, my last time step value, which is my initial guess, should be close enough to my next time steps value, right? So we can actually scream. For example, if I-try is equal to 4, I'm going to like scream at something like display something goes wrong, right? So we'll try this again. Oh. So maybe we increase that by something to 8 or something. Let's do this again. Okay, so there are some cases where 8 is not even enough. Let's try 10. Huh.
Your if statement is only to 4.
Oh, yeah. My if statement is only to 4. So, right. Let's do this. Right, nothing goes wrong this time. And let's plot it. Right, so it doesn't seem to change much. Right. Yes.
So if you were increasing